Great. Hi guys, so I'm basically doing an introduction to analytic number theory. This is not supposed to be much about learning techniques. It's basically getting nice results so that I can advertise the subject. Regardless, I hope you enjoy the process of deriving the results anyway. So what we're going to do here is, the general theme of what we do here is take a sum and you try to approximate if you can't do like let me write this properly. So you approximate sums which you can't evaluate exactly so that you just get a rough idea of size. Approximate sums, really that's all we will be doing. Sure, this is getting bad. Is it readable? Should I just use Notepad instead? How do we do the approximation, by the way? Like, is it analytic? So the thing is, we go from a sum to an integral. So we'll first discuss the tool which takes sums to integrals, and then we'll start by evaluating something basic like summation of 1 by n. And as time progresses, if the lecture time permits, I'm planning to cover summation 1 by primes. This is supposed to be prime. So what happens if you add the reciprocal of primes less than equal to x? What did that look like? Then we compare it with a familiar sum and then try to see what it insists, what the size of any particular, like say nth prime should be. So before that, we start with the tool for this. So let's see, there's a function small a n to c. For our purposes, it's probably going to be n to r, but it's okay. We define capital A of x. This goes from r plus to c. We define this to be, this is an arbitrary function, by the way. This can be any function. This is defined by capital A of x equals to summation n less than equal x small a of n. So it's going to look like a step function. Let's say this could be your, wait, so this is your x, this is your capital A of x. So it's step function here. It only changes values at the integers. And so on. That is what the capital A is supposed to look like. I hope the picture helps. So
it's natural numbers also
should I think? Actually, give me a second. I realize there are some audibility issues. I'll get my headphones. Okay, just give me a second.
okay.
Yeah, right. I'm back. Please repeat.
I said since A of n is from natural numbers to complex small a of n, then I guess the step function should add up.
Wait, I didn't follow. Oh, right. You're saying that it should be 0 here, right? This part would necessarily be 0.
No, no,
Is
I'm
that
not
what you're
saying that.
saying?
No, no, it will not even take output from
Wait, for some reason I can't follow what exactly you meant you say.
ignore for some time. In case I said something wrong.
Okay. So I can move ahead, right?
Yes.
Great. So here is what we want to evaluate. Uh, Okay, this is not the only thing. You also have another function f, which is integrable. That's all we care about. It's again R to something, let's just see. I'm mentioning C every time as a technicality, but we'll really be only dealing with real numbers. We won't go to complex numbers. So here is what we want to evaluate. Summation n less than equal to x, a of n, f of n. Before before I state the thing, the obvious question is why would you want to evaluate it? Like maybe just look at the full thing as one term or something. What's going on here? Okay, this is integrable. So philosophically speaking, when you use what I'm going to show right now, uh, you want to look at like the the function f sort of acts like a weight of sorts. It's like an is somehow the main thing and f is sort of subsidiary, if that makes sense. Anyway, uh, let me write the thing in back like it's a main sort of lemma, so I want to give it a different color. Summation n less than equal to x an fn. Yeah. So here's what I claim. I claim this is equal to uh wait, let's change this to summation y less than equal to n y strictly less than n less than equal to x. The notation might look a bit uneasy, but yeah, unfortunately I read it from a bad source and now I'm used to it myself. So right, so this is equal to capital AX f
Which
x.
takes the y, a of n or f of n?
Hmm?
Which of them takes y? You haven't like.
Wait, these are both n, right? So n varies in this range.
Oh, sorry, sorry. Got it.
Sure, the cursor got stuck. Right?
Could you tell me why we are doing this? Like, what are we aiming for over here?
What we are aiming for is approximating sums whose exact values are hard to determine. So the idea is, once I write the full thing, it would be much more clear. Give me a second. So the issue is this tablet which I have here, it's a bit new. So it randomly decides to stop moving the cursor. So what I have to do is plug it out, plug it in again, which will take up some amount of time. I'm very sorry. Yes, right. Equals to x. Okay, this thing is going bonkers. Minus capital A y f of y minus integral y to x. I remember y is the smaller number, x is the larger one. Oh, I think it is 80 dash a, right? Yeah, a of t f dash t dt. This is what I'm claiming. So yes, the idea generally tends to be this thing in green over here. I select it. So this generally tends to be like a nice kind of term and is generally the large part. And these tend to give us some small parts which are like these are the not nice to evaluate parts. So we just declare them as a sort of error term. How we declare them error terms, again, there is a formal way to do it. We'll discuss it. But yes, do you get the idea of what we're doing here? Like if this relation holds true, we'll prove it right now. Do you see why this could be helpful? Like here's a huge nice term which is this is the approximation and this will serve as the error. That is the idea we're going with.
Clearly, the integral will be negative, but we can't declare it negative here because we don't have a of t to be integrable on y t, like x.
All right, the sign issues will sort themselves. That is fine.
Okay.
Yeah, and in general, just see if f dash is a decreasing derivative combined with the minus sign, this will give you the large term anyway, right?
Yes,
Or
surely.
or sometimes what happens is you're generally taking summation n less than equal to x, right? It's not very common practice for y to be something large. In that case, what happens is the error term is just this AYFY thing, and AXFX might also be the large thing. That is fine. So yeah, let's just start with the proof. I don't know if I should go into the details of the proof. I just realized it's 7:15 already. Uh, hmm. Okay, first for convenience, we will declare. Uh, since this is a step function, you need to deal with the integers. Let a be the greatest integer function of x, m is the greatest integer function of y. Uh, so if you lose track in the lecture, just remember uh, y comes before x in the alphabet, y comes after x in the alphabet, m comes after k in the alphabet. Hopefully that helps you keep track. So summation y less than equal to x an fn is equal to first how do we write this? Right, you can just write it as summation n equals to m plus 1 to k an fn. Why m plus 1 to k? Y strictly less than n. So this forces the smallest n that can work to be a ceiling of m plus 1. There's a slight amount of casework there if you want to convince yourself. Like what if y itself is an integer? Then you'll be confused. Do I take ceiling plus 1 or do I take floor? You, or sorry, if you want to take floor plus 1 or ceiling, floor plus 1 is what actually turns out. You can check, it's easy casework. Right? And now the largest integer n can take is restricted by x. So by definition of a floor function, k is what caps the value of n. So that is fine, right? After that, there's going to be a decent amount of algebraic manipulation. So don't want to waste much time here. This uh, equal to relation n equals n plus 1. One thing I've realized is the final goal I want to establish is going to take too much time. 2 weeks later, I might have to do a lecture too. I hope you can bear with that. Okay. En can be written as, see, Our final expression does not have a small a. I want to introduce a capital A. Capital A of n minus capital A of n minus 1 fn. This makes sense, right? Like you can just do a graph. This is an is supposed to be uh,
Yes, yes,
summation till.
yes. Got it.
Okay, that is clear. Cool. Then you just take it as summation uh, n equals n plus 1 to k a n f n minus. Yeah, basically just breaking the bracket, taking this term here, taking this term here. Minus summation n equals to m2 k minus 1 a n f n minus 1. Wait, no, a n f n plus 1. I'll just look
We
at what I
flip
did with the indices a
the
bit. Huh?
we flip the variables. It should
Uh,
be n minus 1, I guess.
all right, that's what I'm saying. Here n started with n plus 1. That is exactly what I was talking about. Now starting n with n here, right?
Oh yes, you
So
changed the sign.
this will
Okay,
go up by
okay,
1,
right.
n minus 1 to n. That n will go up by 1, f n plus 1. The indices are different here, right? Should I highlight that? I'll do it because somebody else is going to ask anyway. Wait, brilliant. Okay. Sorry, it's just it's going a bit slow because this cursor is lacking so much. Oh my god. Yeah, this is the last expression on top. What do we do next? Hmm. We need to introduce the integral thing, right? How do you do integral stuff for a step function? Okay, no, that is not
Can we
how.
try to approach it through Riemann sum?
Okay, if you happen to be familiar with Riemann sums, this is almost immediate. What you'll have to do is,
Yes,
by
yes.
the way, for people who are not familiar, the next few seconds just filter it out of your ears. It's absolutely not relevant to you whatsoever. And we won't need it for any deeper understanding. It's just shortens algebra. If you're familiar with the Riemann-Stieltjes integral, which is like this thing, right? Y2x f t d a t. You can directly write it like this. I hope you're talking about the Riemann-Stieltjes integral, not the normal Riemann integral.
I was talking about Riemann sum, which was introductory to integrals.
Oh, okay. Sorry. It's just I have not seen the
But
entire class.
can you explain this? I guess I know.
Huh?
Can you please explain this? I guess I know this.
All right. This thing. So this happens to, yeah, this after a biparts will directly evaluate to uh, fx ax minus fy ay minus integral y to x at dft. Oh yeah, the expression is not clear, but yeah, you get the idea. If you're familiar with this thing over here, which I've done, then that is a very good shortcut. Otherwise, we have to do this tedious thing, which I have
Yes,
exactly
but
9.
how will we convert the sum? I guess.
Huh?
Oh, I got it. I got it. How will we
Yes.
convert? Yes, yes, yes. It
The
makes
final
sense.
expression on top has F dash. Wonder where that
Yes,
came from.
it is the same.
Right.
And now can you explain through that simpler method that you told?
It's simpler if you know some more advanced integral stuff. It's not the class 12 NCRT integral stuff. I did not put that up as a prerequisite. So maybe we could discuss that one after lecture, but not here.
Okay, okay.
Right. That's not the normal Riemann integral.
Yes, yes, I
It's
know.
not. It's not exactly like substitution or something. So yeah.
Yes.
Oh, who was this by the way? So that I remember who to talk to next time. Never mind. I'll continue with this.
What
Hopefully
did
the
you ask?
hmm?
Did you
Nothing. I was
ask
asking
something?
who asked the doubt. That's all.
Oh, I'm on Rag.
Okay. Anyway, uh, okay, wait, too many people leaving the column. Sorry, guys, I won't digress anymore. I'll continue with the normal high school thing. You may resume listening. I'm sorry. So we were here. Summation n equals n plus 1 to k, capital A and Fn minus, yeah, this thing. Oh, wait. Uh, yes, now you can write this as summation n equals to m plus 1 to k. Let me check the indices. I want to be a bit careful. Yes, k minus 1 a n f of n minus f of n plus 1. Where does this come from? I took the common terms here, like only with the indices. Like m is an index here, which is not here. I'll consider that later. But m plus 1 is an index in both, so I've taken that term here. You get the an, fn, f of n plus 1 that shows up here. And n plus 1 had a minus before it. I kept that here. So the common indices go up to k minus 1. Now we'll write the terms which are not in the common indices separately. That is plus ak fk minus am fm. So do you see we almost already have the form for the like things outside the integrals over here essentially. This is mostly what we wanted. We can do some tweaks over there. We just want an integral sign over here. But if you're familiar with calculus enough, I think you've seen this fellow
We
before.
can directly convert this into that integral.
Yes, this is precisely integration from n to n plus 1 f dash t dt. This is where you get the integral from. Oh no, wait, this is the negative of that. You have n added and n plus 1 subtracted. So minus that. Let's take up more space. It's starting to look ugly. Yes. It's equal to summation n equals m plus 1 to k minus 1 capital A n integral, correct, minus assumption integral n to n plus 1 plus this, right, f dash t dt. Hmm. Oh, nobody corrected me. This is not fm, this is fm plus 1. This term came from here, right? So here you have an fm plus 1 dt plus hmm, Yeah, I don't think I'm getting some. Yeah, I just do it in the next step. Let's not do all of them simultaneously. K, K, K minus A M F M plus 1 equal to, okay, might as well write this thing directly at this point. Integration, where does this go from? Smallest n is n plus 1. You start with n here. So m plus 1, the largest thing it goes to is k minus 1 is the largest n plus 1 is the largest point. So k, n plus 1 to k, a of t f dash t dt plus a k f k minus a m f m plus 1, right? Does this make sense so far?
Yeah.
Okay, great then. Hmm. It's equal to, now you see the m plus 1 and k are very close to the exact values we want. We want y and x over here, right? So we just add and subtract that and let's see what happens. Equal to, so what do we want here? We want y here, we want x here. So for y, this is m plus 1 is a bit above y. We want to add the integral y to m plus 1 part. T t dt plus, what else do we want to add? We want to add the k to x part. K to x dt f dash t dt plus what we already had. And we subtract this later. K dt f dash t dt plus a k f k minus integral k to m a d f dash t dt plus, wait,
Did you intentionally switch the M and K here?
huh? Wait, did I
Uh,
switch? Wait,
like in the last integral, did you did it intentionally?
right, I just realized this is supposed, wait, what? Wait,
Okay,
wait,
okay, no problem, no problem.
this is supposed to be, this is supposed to be k to x, right? Right. Like I added some terms over there. The first two terms were added. I'm subtracting them now. Yes. Supposed to be adding both the terms, right? Just making sure. Give me a second. I'm just doing the sign check.
So two lines before, shouldn't there be a negative sign before the integral?
Wait, where exactly?
Like the integral shouldn't it be negative integral m plus 1 to k?
Oh, here.
Yeah.
All right. Right. This is why I was messing up with the signs. Right. Thank you. Yeah, k to x was negative.
Can you give some time to write this whole equation down?
Huh?
Can it
Okay.
take like a minute to write this down?
Sure. Oh, by the way, in the end, I'll share a PDF for the full thing.
Okay, but it's still lagging.
Yeah, I'm not saying that's not a reason for you. I'll give you time. Don't worry. I think this is also supposed to be negative. Let me check. Right. This is also supposed to be negative. Now everything makes sense. That's integration y2 plus 1. Yes, and finally this thing is not breaking down every single letter. Right, great. So this thing on top, the entire first line, you might identify it as,
You like forgot that am minus fm plus 1 term.
oh yes, I forgot that.
No problem.
So many things are missing. Yes, the algebra is a bit messy. And as I said, there's a neater way to do it, but it requires too much information on integrals. Series, yes. Equal to integration. Yeah, this is not just integration y to x, negative sign. You have y to m plus 1, m plus 1 to k to x. And these three are the consistent negative
Can
sign.
I guess what are you going to do next?
Huh? Yeah,
Can
sure,
I
feel
like
free to.
yes. So I think you will just try to convert the integrals into some kind of constant term and then make akfk to axfx minus amfm
Yeah, right.
plus n
That's
into.
essentially what I'm going for.
Yes. Okay.
Because everything has come along, right? AK, FK is
Yes.
very close to what we want. So we make it exactly
Yes.
what we want.
And we still have that a is some kind of step function. Then we can try to take it out for some real values
Oh, wait, are you talking about the applications of this lemma or the rest of the proof for the lemma?
or rest of the proof of the lemma.
Rest of the proof. Yeah, sure, essentially. ATF dash T PT plus. Hmm. Um, I mean, I was planning to write the next step directly, actually, but let's discuss. So, is this exactly?
N to x,
So
right?
you can now take this out. This, huh?
Integral n to x atf dash t, right?
Wait, where exactly?
The second term in the first line and the second term in the second line. We'll pair them. Switch the sign in the first term by switching the order of integration. Order of limit, sorry.
Wait, you're talking about this term and this term, right?
Yeah, we can pair them up, right?
Uh, I added and subtracted these terms on purpose. I
Oh,
don't
okay.
want to cancel them. I'll do something with them.
Okay, fine. Sorry.
Yeah. So these two terms were added and subtracted. These two terms were added and subtracted. Oh, by the way, don't forget this fellow. I just forgot writing it last, so I just squeezed it in somehow with the minus sign. Yes. That's clear, right? Now, here, A, K, F, K plus integration K to X. In this entire duration K to X, the greatest integer function of T is always K, right? It won't become K plus 1. That will require X to exceed K plus 1. But that can't happen because of definition of K. The definition of K, it's already greatest integer of X. So like if this is 5, then X is equal to 5 point something, something, something. So greatest integer function of T is never going to become like 4 or 6 or anything like that, right? It's always 5. Which means A of T, which means small a is constant, right? That doesn't mean capital A is constant. Wait.
But the capital A like remains some kind of constant if you try to approximate.
Right. It does remain constant. I don't know what I was thinking. It is. It very much remains constant. As I said, it's a step function. It will only change between integers.
And yes, then we can easily integrate them
Yeah.
because
But
we have object.
since greatest integer t is constant, since that's the case, we just take it out. K integration k to x f dash t dt minus a m f m plus 1 integration by 2t. Wait, what did I write? Goodness. Yes. Yeah, you can first take this out. This will also remain between uh, m almost all the time. At exactly m plus 1, this thing becomes m plus 1. But since that's like at only one point, it's practically m for all the places. We can take out an a of m from there. Does that make sense? What I'm going to do with this integral?
Yes, it makes sense.
Okay, cool. Okay, it's 7:40. So we have spent a lot of time doing the grunt work stuff instead of going to the results. Oh no. So a of m integration y to m plus 1 f dash t dt. Since you spent so much time here, you can see how these two evaluate, right? This is just,
So just to make this equation fancy, we just convert like a of k into a of x and a of m into a of y.
yeah, you want a neater form, right? Because the
Yes,
uglier
yes,
your
yes,
algebra is, the less insightful it is and the harder it is to
yes,
do manipulations.
yes, makes sense.
Like, technically speaking, you could use it this way, but just I'm tidying up the terms. We are done with the grunt work the moment we added integrals, the moment we got this fellow. Main work was done there and then. I'll directly write the result from here, a of x. Like you'll technically get that with a of k here, but a of k is a of x, we discussed. X, fx. Any details here, I will. Yes, I should leave it for verification for you. Right. Saves me time and gives you a bit more idea of how the proof really worked. A d f dash t dt. Right. So, for the start of this lecture, we will deal with a very simple case where let an congruent to 1. What does this look like? Integration, summation. What does an look like? An is this greatest integer function of n, right? Uh, hello.
Yes, a and integrated.
Yeah, great. So, what is summation y less than n less than equal to x? Please just bear with me a little bit. After the simplification, we'll actually put the result to use and get something, get an approximation. Finally, going somewhere. Just a little bit, please. En fn is equal to just summation y less than n less than equal to x. Congruent to 1 means it's 1 for like every single value of n you're going to give. F of n, that's all it is equal to, look at this term over here. Keeping these terms inside, will help, because honestly, nobody remembers the exact expressions so much. And this cursor has hung up again. Right. So yes, having the exact expression helps. Refer to it as a dual algebra. En is greatest integer n, so this greatest integer of x, f of x, minus greatest integer of y, f of y, minus notation of y to x, greatest integer of t, f dash t dt. It doesn't look very different, but the thing is, for this particular form, since you want to look at these things at error terms, right? We can throw more things inside an integral, and we can make the error term thingies a bit smaller. Basically, just make the expression nicer, that is all. Just a bit nicer. Hmm. And what we have to do, give me a second, let me try to recall the details. Hmm. Yeah, so what you do is,
Can we
uh,
just integrate the parts to make this integral a
yeah,
bit
that's
nicer?
what I'm doing. The pi parts is what you have to do. So you just write it as, uh, here's the thing I'll use. Integration y to x tf dash dt is equal to, so by parts, I hope you guys follow the by parts. This is being differentiated, it will become 1. This is being integrated, so it just becomes ft is equal to x f x minus y. Is it fine so far? Like, I have not given you the full simplification statement yet, in case you're still wondering. Minus integration y to x x. So basically what I'll do with this is, I will write this as uh, t minus greatest integer function t. So the integral will contain this ugly term. This thing simplifies as I showed. And I'll just write the final statement for you, because I have a gut feeling that just doing algebra without purpose is boring you guys. Uh, yeah, just summation y less than n less than equal to x f of n equals to integration x y to x f of t dt. Now I hope the approximation looks a bit more like what you wanted. Like, you take the summation over an integral and approximate it. Yeah, you take the summation of the functions plotted over an interval, and you sort of approximate it with the area they cover. That is sort of what is happening over here. So I hope the final expression is a bit intuitive. That's integration y to x t minus greatest integer function of t f t. Wait, this is f dash t. This is f dash t dt plus fx minus fx, x minus greatest function of x, plus fy, y minus the half of y. It's actually best if you just introduce fractional part of x equals to x minus x, and we simplify these. X fractional part of x plus f of y fractional part of y. So you see the things outside the integrals are even smaller. Earlier you had a greatest integer, now you have a fractional part. And things inside here generally behave well. That's the philosophy. Even if it doesn't look very nice outright, once it's inside the integral, it's still easier to manipulate. So I'll give you a 1 minute break to if you want to revisit any algebra or whatever. But the end result is really what is more important, because now we're going to begin using this to approximate stuff. We'll start with a very basic thing. You know how summation 1 by n is essentially log n. How close exactly? We'll do a more detailed analysis using this lemma over here. How close to log n do you exactly get? Actually, yes, do this. Then I'll discuss how we talk about error terms. Yeah, yeah.
So we like use this lemma to approximate many sums.
Wait, we don't approximate integrals. We approximate using the integrals. The
Yes,
sum is
yes.
supposed
I'm
to be the
asking
annoying.
if we approximate the sums only.
Yes, yes, yes. Oh, okay, just do this. Right, great. Okay. Should I proceed? I'll just talk about one more technicality, which is like how do we talk about the error term? Oh, yeah, I'll just start, I guess. So, big O notation. Here's the idea. Fx equals to OGX. What does this statement mean? Implies by the definition of big O, that there exists C belong to R such that for all, this is a notation for all large X, Fx less than equal to C G of X. We'll discuss this thing with some examples, of course. Yeah, right. And this, of course, means you want F and G to be like defined till like infinity, starting from some constant. Otherwise, the notation doesn't make sense. Hmm. So for example, x equals to ox, because there exists a very clear constant, c equals to 1 just works. 5x is ox.
C is greater than or equal to 5 works clearly.
Yeah, c equals to 5 works. Root x equals to ox. I said for all large x, right? Once x greater than equal to 1, c equals to 1 works. Right. You could do something like the log x equals to O of x square. Nobody is going to kill you for using bad bounds. Now, what you cannot do is say log. Uh, you don't necessarily need to throw in an x. Suppose 1 equals to O of e to the power x. Something stupid. What you cannot do is log x is not equal to O of 1. No c exists. No c exists, which does our job. So it's like you need to be equal to the function up to a sort of constant-ish size. You know the size of the error term. You can just talk about O of like bad function equals O of nice function. And it tells you error size is roughly equal to nice function. And you get a better feel for it. Does this make sense? If you have any queries, like maybe even specific
Okay,
examples where you're not
wait
sure how to
here.
compare.
Can you just repeat the statement you just stated? Sorry for not paying it much attention.
Which one? Is it like the big or in general, or is it
Or
specific example?
like you tried to say that the error is very small by this O of X definition.
Yeah, for example, there is a very bad function, but you only care about its size. Like f is a very bad function. You don't, but you only care about like the rough size of f. So what you say it's OGX instead, where G is very nice. This is say
So you
a
will
very
convert
weird,
to
uncomputable function, some thousands of summations and log something weird. And this turns out to be, I don't know, something x square maybe.
so you
You
just try
just
to
say this is
convert.
OX. Hmm?
So you just try to convert. So you can get better sums and approximation.
Yeah, you just give a function which is roughly the same size, or maybe slightly larger,
Yes,
something
yes.
like that. It just has to be
Okay.
nice so that you know what the error looks like. That is what you want. You don't want exact values for the error. So
Yes,
that
but we
just
can
makes
get
life
some
easier.
approximate.
We don't care about the exact value of the small parts. That is the whole theme that we focus on. We want to know the size of the large relevant parts. That's it. Small things can be dropped. Now, now that that is established, congratulations. I finally have like real stuff for you. We will approximate summation n less than equal to x 1 by n. Now our tool requires us to write it in the form of summation y less than n less than equal to x. So first choice we might want to make for y would be y equals to 0. But as you start writing the terms out, you'll notice something, right? Like we approximate this using our first lemma. Let me take sort of photo for this. How do we do that? Yeah, actually, let me write the full thing again just in a different thing just to make things easier. So that it can be sort of highlighted every time I copy paste it. Okay, this is too bright maybe. Yeah, just stick to black. Yeah. Summation y less than equal strictly less than equal to x f of n is equal to integration y to x f of t dt plus integration y to x. Yes, I do not expect you to ever remember the formula at any point. I expect you to have it noted down somewhere to refer. Memorizing this will get you nowhere in life. And I also hope you to get a better graphic tablet when you purchase one. Goodness, this lags so much. I'll cry at some point.
Isn't it lagging because you broke it or something?
No. There was a previous pen which I broke, but then I just bought this one. This is brand new. And the tablet is intact.
Oh,
Probably because the pen is new. That is probably the issue.
For the whole time, I was thinking you were writing from mouse.
Goodness, I'll never write that well with a mouse. You should see my previous two lectures for what happens when I write with a mouse.
Sorry to
I
say
can tell you
it, but
tales.
I just thought that you were writing from.
I think they're complimenting on your handwriting. So good.
Don't take it as bad. Sorry.
That's the disturbing part. This bad handwriting should not get complimented. That is concerning.
The complimenting word was sarcasm, by the way.
Right, right.
Joking only, by the way.
Uh, so now I can copy paste this whenever required. So I just start writing terms down. You notice an immediate oh, but just select it and change color. I rewrote the whole damn thing. My life is a lie. Anyway, you can integration 0 to x 1 by t dt. You're about this far. Do you already see the issue?
Zero.
Right, you have a 1 by 0 over here. The function looks like this. And the area underneath this thing, this just goes up to
Maybe try to take
infinity.
some J,
This
J
area
which is.
just
I'm saying just try to take some J greater than equal to zero.
right. That is what we plan to do. So the thing is, this summation starts from 1 and we can choose y to be any real. So this leads to an error. How we fix this error is we just get as close to 1 as we want. So we just let y equals to 1 minus epsilon. See, if the person in front of you is a person of culture and they want to denote something small, they will use epsilon. This is supposed to denote a small number anywhere in your life, not just this lecture. Please note that down. Right, so now when you start writing things, here's the formula for reference. It's too high up. Yeah, now when you try to use the formula, this will lead to integration 1 minus epsilon. Of course, the point is once things look nice enough, you actually set epsilon to exactly 0. Because this thing is sort of continuous if you put a limit. I won't get into the pedantic details. This is x. You want n less than equal to x. That's there. Let's follow. 1 by e dt plus integration 1 minus epsilon over x oh, t minus
You can
floor
leave
of
floor thing easily there. It just closes down to zero.
t. Oh,
Oh no,
can you
sorry, sorry.
can you
Sorry.
just tell me what the derivative of f dash t is?
What?
It's a just a derivative of f dash. Just tell me what f dash t would be here.
F dash t hit ln of x,
Are you sure?
ln of t. Sorry.
Okay, cool. Turns out you're off by a little bit. That turns out to be the integral of ft. If your ft is 1 by t, you can check from any calculus book, f dash t turns out to be minus 1 by t square. So
Oh
you have
really?
a t
Sorry, I
square.
didn't think that I took integral as derivative.
Yeah, right, so it happens. I didn't provide any calculus resources. I'm very sorry. Yeah. So this becomes a minus. And then you have the residuary terms. Yes. What do you have here? Okay. All right. I put it here so that I don't forget, and then I just never mind me. Wait, this is minus, right? Minus greatest integer x by x plus greatest integer 1 minus epsilon y 1 minus epsilon. Hmm.
I just noticed that the fraction part would be the same.
Yeah, right. Control x is right. Yeah, gone from my side. Now that we have written down that pathetic algebraic thing, from here our life is somewhat simpler. First off, let's just set epsilon tends to 0. So this becomes integration exactly 1 to x 1 by d dt. If you're not familiar with the idea of limits, I'll have to be a bit hand wavy about it. Just think about what the terms approach as you take things to epsilon, right? Do not plug in the exact values. Minus this thing remains exact. X plus fractional part of 1 minus epsilon. As you make epsilon reach 0 is 1. It never becomes exactly 1, but it gets very close to 1. That's the idea. Again, people familiar with limits, I don't need to elaborate. People not familiar with limits, any amount of elaboration won't help. Just take my word for it. We can throw in one approximation right now. This thing, fractional part lex, by definition of fractional part, is less than equal to 1. Implies uh, fractional part of x by x is O of 1 by x. So this is
It
1
just
is,
tends to be zero if you take some large bits.
yeah, but I want more than tends to 0. I want how fast does it tend to 0. So that is preserved by O1 by x.
Yes, yes. We will convert this.
Goodness, this tablet is going bonkers. Now I'm getting a notification which says Windows does not recognize said device.
Did you not configure your new pen with the tablet?
There's not much to configure with the pen. The tablet requires a driver, but that's it. The pen is supposed to be a passive device. It doesn't even use electricity, goodness.
Or driver issues are really bad in Windows. I will say just don't use it.
Is everything clear?
Anyway, let's continue with this. Once my graphic tablet allows us to, integration 1 to x 1 over t dt is equal to, this is something nice. Can somebody tell me? Yeah, I'm actually not going to write it if you don't tell me.
Log x.
Right. The integral of 1 by t I just mentioned is log x. This is array. Doesn't let me write a full letter again. Log t from 1 to x. God, Lord. Is equal to log x minus log 1, but this is just 0, is equal to log x. So, summation n less than equal to x 1 by n. I hope you understand when I say n less than equal to x, I mean natural numbers, not whole integers, is equal to log x plus integral 1 to x t minus t by t square.
Or maybe just
dt.
notice that this integral is somehow close to 0. I was saying that t minus flow t uh, means it tries to approximate.
It doesn't tend to 0, it actually tends to some non-zero constant.
Yes, yes.
Right, this is correct, right? I just want to make sure the algebra so far is correct. Yeah, right, it probably is. Cool. So what did you get from that? That
You forgot the big O.
I didn't forget the big O. Remember, whatever I write, however this lecture
Oh,
proceeds, entirely by my tablet's discretion. I have no say on it whatsoever. I have lost
okay.
all authority to a stupid tablet. This 1 plus O 1 by x. The 1 minus epsilon thing is still giving us plus 1. Right. Now, I would like to say we are done, but technically this thing depends on x. We don't want any nice terms depending on x. Like that beats the whole purpose. So what I'll do is integration 1 to x t minus gift over t square t is equal to, this thing is generally very risky, and here we are going to discuss how we figure out if it's doable. 1 to infinity t minus it is t over t square dt minus integration x to infinity t Why am I still writing this? Did nobody bother suggesting it? Aatman, maybe you introduce the fractional part. Actually, consider using the fractional part sincerely, audience. This makes expressions so much nicer. Or did I bore you guys too much for you to bother responding? In any case, so here's the idea. We'll first show that this integral grows so slowly so that even though I take the limit to infinity, this thing will turn out to be bounded. And this thing will turn out to be small. We'll quantify small later. We'll quantify it with a big O. Also, let me make this big O like actually big. There is a reason we call it big O, because we use two kinds of O's and little O is a thing. We don't want to mix them up. Don't care about what a little O is right now. We don't need one right now. So this is the idea. Do you guys follow so far?
Yes.
Okay, great. How about others? Let's try to not run on one response.
Yes. We follow.
Cool. In that case, we'll again use the stupid bounding of t. Oh, wait, how much is this? Yeah, this is less than equal to 1 implies t by t square is less than equal to 1 by t square.
Oh, this is a converging integral. Yes.
Huh?
Yes, this is a converging integral. We would have much more
Yes.
now.
Yes, I hope I have drawn enough attention to the fact we are discussing whether taking the limit to infinity here makes sense, essentially. Makes sense is important. Before that, let's talk about what does not make sense. Integration 1 to infinity 1 dt. This does not make sense because, technically speaking, what you're doing is extends to infinity integration 1 to x 1 dt. You're not allowed to do this if this entity, if this limit tends to infinity, you're not allowed to write these things. So here I'll verify that. This is greater than equal to 0. I show that it's less than equal to constant, then it's a very well defined thing. It's another constant. Integration 1 to x 1 over t square dt is equal to minus 1 by t from 1 to x. This is equal to 1 minus 1 by x. Yes, be careful here. There's a lot of signs. Minus 1 by x minus of minus 1 by 1, which is plus 1. Now as x tends to infinity, this thing tends to 1. This is very well defined. Well defined. All that remains is bound this term. That is, as it turns out, simple. Again, use again the very stupid bound fraction t by t square less than equal to 1 by t square. Now given t belongs to, given t is greater than equal to x, look at the bounds on this thing. Goes from x to infinity, so t greater than x implies 1 by t square less than equal to 1 by x square. Implies integration x to infinity 1 by, wait, am I doing something sane here? No, wait, forget this, forget this, forget this. Hold it here, yes. Integration x to infinity 1 by t square dt second minus 1 by t from x to infinity. This is just 1 by x. So this thing, this term is always positive, so the integral will always be positive. This is between 0, 1 by x. So what we can say is equals to 1 by x. So finally we have our complete result. Summation 1 less than equal to and less than equal to x 1 by n is equal to log x plus integration 1 to infinity. Why are these things fine? Because it's a constant. You know it's a constant. So later, you can always use numerical methods to use this whenever you care, but this 1 plus O of 1 by x we got here, plus another O of 1 by x, which this is from the 1 minus epsilon thing. This is the integral. Now you see 2 by x is also O of 1 by x. Like if you have a C1 by x bound on this and you have a C2 by x bound on this, the full thing can be bounded by C1 plus C2 by x. Basically, the big O notation sort of combines very nicely. I don't have to look at the exact error terms. Right? The full thing is O1 by x. This is the great grand formula we have come up with. Goodness, let me. Yes, thank you. So now, oh yes, by the way, as you've noticed, we had allowed, no, the graphic tablet has not allowed me. Oh, yes, we had allowed these y and x to be arbitrary reals. Goodness, I'll just use my pen. I'll just use this to scroll. Right. So we can let this x be any real number and our entire bounding works. And if you don't like this thing, just call it c. Log x plus c plus error term O1 by x. So you know that the error in this expression also grows like 1 by x. You know how fast the error decreases. More importantly, you know that the error decreases. The error might even increase. Who knows? The error you might have had here would be OX or O root x, maybe something. this grows as you increase x. So you at least know that you take a larger x, your approximation becomes better. So you know how approximate it is. We have quantified that.
Yes, but sadly we can't do today that one by times.
Yeah, right. Summation of 1 by primes. I don't know if I can do it even in a second lecture if we progress at this rate. But okay. I at least showed you guys the tool and what it can do. So any
It was a
opinions you
really
have?
powerful tool, I guess.
Sure. Did you guys like it, or like was proving the full thing like too boring before it got to summation 1 by n itself? More importantly, should I do a recap before we end this? Hello? I'll take the silence for a yes. Right, skip this. Yeah, we essentially just prove this big lemma. Should I delete the rectangles at this point? They're probably making it hard to read. Yes. So we first prove this lemma with weighted sums. I haven't put it to any use, so it looks worthless right now, which is fine. We proved a very specific case of it here. This is what we actually use, summation fn, where f is a very nice function in the sense it's integrable and everything. So we discuss an integralish form. Then we picked a very nice, very specific n, and then we analyze how things go. How nicely does this let us approximate? Yes, this also tells you that limit n tends to infinity, summation minus log is going to give you a constant term. Also, I think this thing is like something, much is this supposed to be? Approximately 0.43, just the integral. Yes, so I think that's all.
Hello?
Yes.
Oh, I'm sorry. Yeah, okay. Should I stop recording?
Oh, yes. Stop recording. I think I'm done for today.
Awesome.